In the last module, we derived the von Karman integral momentum equation, and just a very quick recap of it. This is how the von Karman integral momentum equation looks like. This was derived for the most general case of varying free stream velocity given by u infinity as a function of x, and for the case of suction or blowing occurring through the bottom wall, solid wall. Therefore, we have a Vw which could be non-zero, positive or negative. This equation, von Karman momentum integral equation, doesn't make any other assumption other than what was used in the boundary layer approximation. So, you started off with the Navier-Stokes equation, you did certain mathematical manipulations, no assumptions, and then got it simplified to a form which was very useful for us, because this equation is now an ordinary differential equation in one independent variable x. Your dependent variable, which was u or v, has now become one dependent variable, which is delta 2 or the momentum thickness. We also have the terms for variation in free stream velocity. Most importantly, what comes out of this equation is a quantity that we as engineers need to use very frequently, which is coefficient of friction, which was shown to us by scaling to be a function of Reynolds number alone. So, that part, what you want as the output quantity, is already sitting here for us. So, if du infinity by dx is equal to 0, which will be the case for a constant free stream velocity, and Vw equal to 0, which would be the case for no suction or blowing, it is a matter of getting d delta 2 by dx is equal to Cfx by 2. Cfx is something you need to write in terms of wall shear stress and Reynolds number. Therefore, wall shear stress would be mu du by dy. So, the philosophy being, you assume a velocity profile. So, du by dy is therefore an expression. D delta 2 is also an expression, because delta 2 is related directly to u by u infinity, which is assumed. So, both these quantities on the left and the right hand side, which is of interest to us, are only functions of u by u infinity, which has been assumed by us. Please note that momentum thickness delta 2, if we go back to the definition, has integral from 0 to delta. Momentum thickness has an integral from 0 to infinity, which translates to 0 to delta and delta to infinity. The second term goes to 0. We are only left with this one. So, when I substitute these profiles, whatever the profile may be, and integrate and substitute the upper and lower limits, you would end up with a delta coming in the expression for delta 2. And therefore, when I substitute for d delta 2 by dx, you are indirectly going to get a differential equation for the boundary layer thickness, which is going to be directly used for getting the coefficient of friction in terms of the non-dimensional quantity of interest, which is the Reynolds number. So, let us write couple of statements about the integral differential equation. So, integral momentum equation is exact in nature, no assumptions other than the boundary layer assumptions. ODE in delta 2, okay, first order, so much easier than second order partial differential equation, correct. So, first order ordinary differential equation does not know restriction on variation of u infinity or Vw. If you look at this, du infinity by dx, let it be any complex variation, does not matter, I would be able to calculate the derivative of this function and use it here. Okay. Displacement thickness, momentum thickness, variation in the free stream velocity, suction or blowing, coefficient of friction, rate of growth of the momentum thickness, which in effect is nothing but the rate of the growth of the boundary layer. So, using this as a background, we will try to get solution for the integrated momentum equation using a polynomial profile. Using a polynomial profile, we will try to get a solution for this differential integrated momentum equation. Let us take the case of a third order polynomial. Second order is very easy to do, that can be given as an exercise to our students. Fourth order will be a lot more difficult to do. So, third order polynomial, let us take. So, polynomial function is u by u infinity is a plus b eta plus c eta squared plus d eta cube, where eta is equal to y by delta of x. Okay. We also assume u infinity is equal to constant, Vw equal to 0, which is no suction or blowing. Okay. Therefore, my integrated momentum equation, we will simplify it later. So, this one was here, du infinity by dx will go to 0. Therefore, du infinity by dx equal to 0. Therefore, integrated momentum equation becomes d delta 2 by dx is equal to Cfx by 2. One term on the left hand side, one term on the right hand side drop off. This one drops off, no suction or blowing. This one drops off because du infinity by dx is 0, because u infinity is constant. Very good. What do I need to do now? I have a third order polynomial. I need to get the constants or coefficients a, b, c and d such that the boundary conditions related to the flow are satisfied. What are the boundary conditions? So, if I have to write the boundary conditions, first one, at y equal to 0, let us keep reminding ourselves of the flow problem. Delta as a function of x, this is u infinity, this is my y direction, this is my x direction, this is my velocity profile. At y equal to 0, u equal to 0, no slip, first boundary condition. In other words, at eta equal to 0, what is eta? Eta is y by delta as a function of x. So, y equal to 0 means eta equal to 0, u by u infinity is 0. Second boundary condition, at y equal to delta, any delta, edge of the boundary layer, u is equal to u by u infinity 0.99, virtually equal to u infinity, that means eta equal to 1, u by u infinity equal to 1. This is your second boundary condition. Third boundary condition, at y equal to, now things do not come out so straight, so easy to the students, we have to explain it a little. At y equal to delta of x, edge of the boundary layer, du by dy equal to 0. What does that mean? The profile of the velocity is such that the slope at this edge of the boundary layer is equal to 0. Du by dy equal to 0. Okay. So, this I have to translate this into eta equal to 1, du by dy equal to 0 at y equal to delta translates to. Let us differentiate. First time we are doing it. This is u by u infinity. So, d by dy of u by u infinity, this is nothing but du du by dy 1 by u infinity into y equal to 0 is 0, or y equal to delta. Y equal to delta means eta is equal to y over delta, therefore dy is equal to delta times d eta. Therefore, this boundary condition would be 1 over u infinity du by d eta du by d eta, and you have one delta also here, does not matter. So, everything goes off. So, this is eta equal to 1 is 0. That means du by d eta at eta equal to 1 is 0. This is my third boundary condition. What is my fourth boundary condition? I need 4, right? A, B, C and D. So, let me look at the x momentum equation. What is the x momentum equation? U du by dx plus v du by dy is equal to u infinity du infinity by dx plus nu d squared u by dy squared, correct. Evaluate at y equal to 0. This is what we are going to do. We are going to write this equation at y equal to 0. What happens at y equal to 0? Please, this is critical. At y equal to 0, u is equal to 0, no slip condition. Again v equal to 0, no slip condition at y equal to 0, no slip at y equal to 0, because this is being evaluated at y equal to 0. U by du infinity by dx is 0, u infinity is constant. So, what am I left with? I am left with d squared u by dy square at y equal to 0 is 0. This is my fourth boundary condition. D squared u by dy squared is equal to 0 at the wall. Okay. So, this is something which I have to use. So, first boundary condition was this, second boundary condition was this, third was this, and this was my fourth boundary condition. I have 4 coefficients a, b, c and d. I have 4 boundary conditions. I will use it now. First boundary condition, u by u infinity is equal to 0 at y equal to 0, that is this 0 is equal to a plus eta is 0. So, all the terms here will be 0, implies a equal to 0. What is my profile again for anybody? This one. This is my assumed velocity profile. When eta is equal to 0, u by u infinity is 0, no slip, therefore, a equal to 0, first condition. Second one, second boundary condition was this, eta equal to 1, u by u infinity equal to 1. So, what is u by u infinity? U by u infinity was this one. So, eta equal to 1, a was already 0, b plus c plus d equal to 1. So, u by u infinity equal to 1 at eta equal to 1 implies 1 is equal to 0 plus b into 1 plus c into 1 squared plus d into 1 cube. Therefore, I get b plus c plus d equal to 1. This is my second condition. B plus C plus D equal to 1. Let us use the third boundary condition. Third boundary condition says the first derivative of u with respect to eta evaluated at the edge of the boundary layer is equal to 0. So, for that I need to take the derivative. So, du by dy needs to be evaluated. And for the fourth boundary condition, we need the second derivative also. So, let us do both. So, du by dy, what is u? U is equal to u infinity a plus b eta plus c eta squared plus d eta cube. U by u infinity was assumed. So, this is nothing but this, a went off to 0, b plus c plus d is going to be there. So, du by dy is nothing but u infinity times b d eta by dy, okay, plus 2c eta d eta by dy plus 3d eta square d eta by dy. What is d eta by dy? Eta is equal to y by delta. So, d eta by dy is equal to 1 over delta. Therefore, I get u infinity by delta, everywhere this delta is going to come out, b plus 2c eta plus 3d eta squared. This is du by dy. Let us keep this as it is. We also have to evaluate d squared u by dy squared, that is u infinity by delta, derivative of this d by dy of b plus 2c eta plus 3d eta squared, which is nothing but u infinity by delta, derivative of b with respect to y 0, this one is going to be 2c d eta by dy plus 6d eta d eta by dy. Substitute for d eta by dy as 1 by d, therefore, I get d squared u by dy squared is equal to u infinity, already one delta is there, 1 by delta is going to come out again. So, I get u infinity by delta squared 2c plus 6d eta, 2c plus 6d eta, or write it in this form, u infinity by delta squared 2c plus 6d eta. This is my second derivative, 6d eta, which is my second derivative. All of these have been evaluated. Now, just have to use the boundary condition substitutions. So, what is the substitution that we make? For the third boundary condition, at eta equal to 1, du by d eta equal to 0, right. So, let us substitute here, du by dy is equal to 0 or du by dy equal to 0, eta equal to 1, I get u infinity by delta b plus 2c plus 3d eta equal to 1, this is equal to 0, implies b plus 2c plus 3d equal to 0. Okay. Fourth boundary condition, this is number 3. Number 4 is d squared u by dy squared at the wall equal to 0. I found out d squared u by dy squared here, evaluated at wall, wall means eta equal to 0. So, d squared u by dy squared is equal to u infinity by delta squared 2c plus 6d eta at eta equal to 0, this is equal to 0. So, I get u infinity 2c equal to 0, therefore, c equal to 0. Life becomes so much easier. We found a equal to 0, we found c equal to 0, we have two equations which have b and d, right. So, I have b plus d equal to 1, here put c equal to 0, b plus 3d equal to 0. So, I can subtract this, I get minus 2d equal to 1, d equal to minus half, substitute this here, therefore, b plus d equal to 1 implies b equal to 3 by 2. Therefore, u by u infinity profile becomes a plus b eta plus c eta squared plus d eta cube is that one, a 0, b is 3 by 2 eta minus 1 half eta cube. This is my profile. Okay. This profile now is what is going to be used for further analysis in terms of calculating your thicknesses which is going to be there. What is my differential equation? This one. So, I need delta 2, I need to write an expression for coefficient of friction. So, let me use this to get delta 2. What is delta 2? Momentum thickness is integral 0 to infinity u by u infinity 1 minus u by u infinity dy. This translates to 0 to delta u by u infinity 1 minus u by u infinity dy, correct? Because the second term from delta to infinity will identically be equal to 0. So, when I substitute that, delta 2 is nothing but integral 0 to delta 3 by 2 eta minus half eta cubed as it is 1 minus 3 by 2 eta plus half eta cubed dy. This we have to do the maths, no matter who does it, we are going to take the same amount of time. So, delta 2 is equal to integral 0 to delta, let us open the bracket, 3 by 2 eta minus eta cube by 2 minus 9 by 4 eta squared plus 3 by 4 eta to the power 4 plus 3 by 4 eta to the power 4 minus 1 by 4 eta to the power 6 dy. Dy is nothing but delta d eta. Okay. So, when y equal to 0, eta equal to 0, when y equal to delta, eta equal to 1. So, delta 2 is 0 to 1, 3 by 2 eta minus eta cube by 2 minus 9 by 4 eta squared plus 6 by 8 eta to the power 4 minus 1 by 4 eta to the power 6. That is it. So, if you integrate this and you substitute the numbers, you get delta 2 is 39 by 280 into delta. The delta comes from here. So, this is just the number, this is 39 by 280, or I get delta 2 in terms of delta as 39 by 280. Okay. So, what are we left with? Now, need to evaluate Cfx. What is Cfx? Tau wall by 1/2 rho u infinity squared. What is tau wall? Tau wall is wall shear stress, which is mu du by dy evaluated at y equal to 0, and we have already seen this expression. Du by dy evaluated at y equal to 0 was this. So, tau wall is equal to mu du by dy evaluated at 0 b plus 2c eta plus 3d eta squared at eta equal to 0. This expression directly goes in here with substituting for eta equal to 0. This goes off, this goes off. I am left with tau wall is equal to mu u infinity by delta into b. I will substitute for b as 3 by 2. Tau wall alone is not enough, we need Cfx. So, Cfx therefore is going to appear here. Cfx is equal to tau wall, which is mu u infinity beta by delta into 1/2 rho u infinity squared. This is nothing but mu b delta by 2 rho u infinity. Take this side. So, 2 by delta, mu over rho is nu, b is 3 by 2 u infinity, and therefore, I am left with Cfx is equal to 3 nu by u infinity delta. My integral momentum equation is now ready for use. So, therefore, integral momentum equation d delta 2 by dx, cancelling out these two terms, constant u infinity and Vw equal to 0, I am getting Cfx by 2 implies, let us go back here, this I will substitute d by dx of 39 by 2 AT delta is equal to Cfx by 2 is 3 by 2 nu over u infinity delta. That is it, we are almost there. So, pull out the constants together, d delta by dx 39 by 2 AT equal to 3 by 2 nu u infinity delta, or in other words delta d delta by dx is equal to 140 by 13 nu 140 by 13 nu u infinity, correct. So, this d delta by dx, if I put this, I can write this as 1/2 d by dx of delta square is equal to 140 by 13 nu by u infinity implies d by dx of delta square is 280 by 13 nu by u infinity. Integrate, I would get delta square is equal to 280 by 13 nu u infinity, there will be an x here, therefore delta multiply and divide by x. So, I would get delta squared by x squared is equal to 280 by 13 nu u infinity x squared. I am dividing both sides by x squared, this will remain as x squared, one x will get cancels. I would get delta by x whole square is equal to 280 by 13. What is this quantity? This is nothing but local Reynolds number to the power -1, and therefore delta over x is equal to 280 by 13 square root re to the power -1/2. When we do the maths, this comes out to be 4.64 by square root of Rex. Remember, our Blasius solution delta over x was 5. This is 4.64. Approximate definitely, but with about half an hour's work of algebra. So, the power this 4.64 will become a better number closer to 5 if we took a fourth order polynomial, which means we would have an additional boundary condition that needs to be brought in. Physical, of course, it should be physically correct, so that we go closer to the exact solution. So, 4.64 by Re to the power 1/2 is the expression for boundary layer thickness delta as a delta by x. Blasius was 5, whatever you got in similarity was in between these two. In the next module, we will continue with this method, evaluate coefficient of friction, and then go to the integrated energy equation derivation and see how it can be used to get the Nusselt or the Stanton number. Thank you.